Well, continuing with our concepts in thermodynamics, the focus of this lecture is on an interesting theorem by Clausius, and then a discussion on how the property of entropy was discovered. So we'll find this bit mathematical or analytical expression and treatment about the concept of entropy. We'll go into more conceptual concept and discussion on entropy later in some other video. Here I have a limited objective in front of me. One is to derive what is known as a Clausius theorem. And second is, once that theorem is derived, show that there is something called as a property, which is entropy, coming directly from this theorem. Okay. So how is this happening? From a conceptual angle, from the analytical angle that we will be shortly seeing. What is this theorem, Clausius theorem? So let me put down this theorem. What it says is that the theorem says that the cyclic integral of, okay, the symbol is for a cyclic integral. The cyclic integral of dq by t, dq by t is this, right? Cyclic integral of dq by t for a reversible cycle. If the cycle is reversible, is equal to 0. It means that if you take a system, and this system undergoes a reversible cycle, okay, and let us say that the heat transfer to this elemental portion is del Q, and the boundary temperature is T, right? Then, if this system undergoes a reversible cycle, then it can be shown that the cyclic integral of del Q by T is equal to 0. So this is the statement of Clausius. It is known as Clausius theorem. Now, how is this derived? Okay, what is the method of deriving this? This we'll see. But before that, let me tell you that this understanding or this theorem has led us to the discovery of the concept called as entropy, or the property called as entropy. Now, how is that so? Before going to the derivation, let me first take this portion, how this property of entropy comes into discussion. So what follows is, if you are talking about a cyclic integral of del Q by T for a reversible cycle is equal to 0, right? It means that if you consider any reversible cycle, let us say if you consider a reversible cycle through a path R1, okay, back to the initial state R2, right? So from some initial state back to the initial state via path R1 and R2, then it means that if you apply the Clausius theorem to this, it means that what you'll get is integral of, where is this? What you'll get is integral of dq by t right, via path r1 plus integral of dq by t via path r2 is equal to 0, right? 0 to 0. So let me call this as some I, and let us say this is f. So this is from I to f. This is from f I. Okay, now just look at it from mathematical perspective. So if I put this on this side, this del q by t on this side, so it becomes a negative f to I, right? And if I remove that negative sign, it becomes again positive I to f. Okay, so if you rearrange these terms, okay, and use our mathematical concepts, what you'll get is that del q by t from I to f via path r1 is the same as del q by t from I to f via path r2. Now this, if you look at this very carefully, you will understand that we have in a way discovered a property. Now how is this that we have discovered a property? What we are saying is that this del q by t is not dependent on the path. So it's not a path function, it is a point function. So if it is a point function, it means that it is representing certain changing property. So del q by t, okay, this del q by t, okay, del q by t is representing certain property which we don't know. Okay, it is representing certain property, and let me call this property as capital S. Okay. So it is representing certain property, capital change in certain property, capital S. Okay. So it is representing certain property whose change is given by del integral of del q by t. And this means SF minus SI is equal to integral of I to f del q by t, right? So this yes is a property, and we can call it as anything. We can call this property as anything. So Clausius, having discovered this property, called it as entropy. So this is the mathematical journey of discovery of the property called as entropy. So how was the property discovered? So first, the Clausius theorem was derived. We have not yet discussed this derivation. So what is the Clausius theorem? Cyclic integral of dq by t is equal to del q by t is equal to 0. This is an inexact differential. So I have put a sign like this. Inexact, or you can also represent it del q. We have discussed this heat is inexact differential. Right? So del q by t is equal to 0 for a reversible cycle. Following which we said that if this is so, by Clausius theorem is true, then this integral of del q by t is independent of path. Because it is independent of path, we said that this has to represent certain property, let us call it as S, property S, and that whose change is given by integral of del Q by T, and that S Clausius called as entropy. So this is how analytically or mathematically we discover the property of entropy. Listen that we are not yet discussed what is the significance of this property of entropy, what exactly it is telling you. We have simply approached the concept of entropy mathematically or analytically. Okay. Now let us prove this Clausius theorem. So we want to prove that the cyclic integral of del Q by T for a reversible cycle is equal to 0. This is to prove this. So there are 3 steps in this proof. So step 1 is we prove that 2 reversible adiabatic processes cannot intersect. This is the first step we'll prove. Having proved this, in the second step, step 2, we will show that a reversible process, any reversible process or any reversible path can be replaced by a zigzag path. Okay. Don't be afraid of these terms. Okay, I'll explain you in a short time what exactly this means. Zigzag path and 3 processes comprising of 3 processes, of which 2 are reversible adiabatics, and in between there is a reversible isotherm. Isotherm means constant temperature process. So this is step 2 of this derivation, and step 3 of this derivation is cyclic integral of del Q by T is equal to 0 by considering a reversible cycle. Okay, for reversible cycle. This is a step 3, which is nothing but the Clausius theorem. Okay, so we would derive this theorem in 3 steps. First is we will be deriving 2 reversible adiabatics cannot intersect. So this proof is very simple. How to prove this? That step 1, to prove that 2 reversible adiabatics cannot intersect. So what is done is that a very interesting trick is done. We would assume that they intersect. Okay, on the contrary, right? So let us say that we'll assume that they intersect. So when you consider that there are 2 reversible processes, and these 2 reversible processes are reversible adiabatic processes, and if they intersect, so let us say this is one reversible adiabatic process, this is another reversible adiabatic process. Okay. Let us say this is A to B. A to B is the reversible adiabatic process, and B to C is a reversible adiabatic process, right? So now if we consider a third process, C to A, so this is A to B reversible adiabatic, B to C is reversible adiabatic. We consider process C to A, which is the isotherm, isotherm means constant temperature, okay, in which there is heat exchange, because it's isotherm, so there can be heat exchange. In the process A to B, heat is not exchanged because it is a reversible adiabatic. B to C is also there is no heat exchange. Now, if I am representing this process on some pressure volume diagram, let us say. So whatever. So you will find that this area which is enclosed, okay, is nothing but the work output of this cycle. Work output of this cycle. So we have now a thermodynamic cycle ABC such that A to B is a reversible adiabatic, B to C is a reversible adiabatic, and C to A is a reversible isotherm. So this thermodynamic cycle ABC is producing work. And what is that work produced? It is the area equal to ABC. Work produced is equal to area of AB, area enclosed by the ABC, right? And how is this work produced? This work is produced by exchanging heat with the single reservoir during the process C to A. Now look at this. It is producing work while exchanging heat with the single reservoir, which is a violation of second law of thermodynamics, KP statement, Kelvin-Planck statement. Okay, so this is not possible. That we cannot have this kind of cycle where there is an exchange of heat only with a single reservoir, right? It is one T cycle, one temperature cycle, which is not possible. Okay, so whatever we have assumed that these two reversible adiabatics are intersecting, this AB and BC are intersecting, that cannot happen. So we have proved that they cannot intersect. This is how we prove. Okay, how we prove? We do an assumption on the contrary and show that if we assume that way, we end up in a thermodynamic cycle which violates the second law, and hence our assumption is not correct. So we have proved that two reversible adiabatics cannot intersect. So this is first step of the proof of Clausius theorem. Step 2 of is that now while you know that two reversible adiabatics cannot intersect, so if you take a reversible path, okay, reversible path, right, and let us say that this is one reversible adiabatic, this is another reversible adiabatic, they cannot intersect. Let us say that there is a third process. Is a third process, okay, and this third process happens to be a reversible isotherm. Reversible isotherm. So what we have done is that we have essentially replaced a reversible path IF with three processes. One is this process I to A, let us say, then A to B, and B to C. Okay, so this is what we have done, right? So now we want to show, what we want to show is that what we want to prove is that a reversible path I to F can be replaced by, means it is equivalent to I to F. It is not if, okay, it is I to F. A process I to F can be replaced by a zigzag path. Zigzag path means consisting of three processes, which are this I to A to B, and B to F, of which these two are I to and B to F are reversible adiabatic, and this one is a reversible isotherm. So how to prove this? Okay, how to prove this? And if we are proving this, then we are very close to proving the Clausius theorem. So what we do is that in order to prove this, we first consider a process I to F. Process I to F. And in process I to F, what we do is that process I to F, which is I to F, I apply the first law of thermodynamics. So it becomes Q I to F is equal to UF minus UI plus WI to F. Okay. Now you consider a process which we want to prove is equivalent. Okay, process IAPF. In this case again, Q IAPF is equal to what? It would be equal to UF minus UI plus WIAF. WIAF. Right? Now let us say that these two works are same. These two works are same. Okay, it means that during the process I to F and during the process IBF, the work supplied is the same. Now, if this is so, then and because these two terms are also the same, right? So it follows that what it follows is that during process I to F and during the process IABF, the heat transfer is the same. Sorry. The heat transfer is the same. Heat transfer is the same. The work transfer is the same. So if your heat transfer is the same, your work transfer is the same, it means that these processes are identical. These processes are identical. It means what? If you take any reversible process, any reversible path, I to F, you can replace it with a zigzag path. You can replace it with the three processes, of which two are reversible adiabatics, and in between there is a reversible isotherm. So making use of this, now we finally come to the Clausius theorem proof, of which we said that if you take a reversible cycle, and let us say that I take a slice of this reversible cycle, so that becomes a reversible path. Or this reversible path, as I had said, can be replaced with a zigzag path. Zigzag path. Okay, so let us say this is A, this is B, this is C, and this is D. Okay, this is very interesting now. You have taken a reversible cycle. You have taken a slice of that reversible cycle, and you have a reversible path in that slice. Okay. So this reversible path, I am replacing it with a zigzag path, comprising of, these are the isotherms. Okay. Now, these are the adiabatics, reversible adiabatics. I am slicing it out. So reversible adiabatics, all these slices. This is reversible adiabatic. This is reversible adiabatic. And in this between, AB and CD, they are isotherm. And why am I able to do this? I am able to do this because I had proved that this reversible path is equivalent to a path having a reversible adiabatic, a reversible isotherm, and a reversible adiabatic. So okay, you see that there is a reversible adiabatic, and in between there is a reversible isotherm. Here also I am replacing this slice, this reversible path, with two reversible adiabatics and a reversible isotherm in between. Okay, so if you look at this carefully now, it means that this path is replaced by a cycle ABCD, and if you give a consideration to this cycle, if you look at the cycle carefully, you'll understand that this is not an ordinary cycle. This ABCD is a Carnot cycle. This is a Carnot cycle. Similarly, what you could do is that you can take another slice. Again, you'll have some Carnot cycle, a third cycle, fourth, fifth, so many. Okay, you can use an infinite number of. So what you can do is that you can divide this reversible cycle into infinite number of. So a reversible cycle is now as good as a summation of infinite Carnot cycles. Okay, and what you know that suppose you have taken one Carnot cycle ABCD. So for example, for a cycle ABCD, Carnot cycle ABCD, you know that del Q by T, let us say that ET is T1 is equal to del Q2 by T2. This is from the Carnot theorem. Similarly, for some other cycle EFGH, del Q3 by T3 is equal to del Q4 by T4. So you can go on doing this for infinite number of cycles. So what we have done is that we have broken this reversible cycle into infinite number of Carnot cycles, and then applying the Carnot theorem now, I can write this as sigma summation of del Q by T. Okay, or because it is a summation for the entire cycle. So instead of writing the summation, I would put a cyclic integral. Okay, cyclic integral of dq by t is equal to 0. Okay, so please understand that how we are getting this. Why we are getting a cyclic integral of dq by t is equal to 0, which is a Clausius theorem. We are getting this because we have broken the reversible cycle into infinite number of Carnot cycles. And why we are able to do is that we are able to do this because we have shown that a reversible path can be replaced by a zigzag path comprising of two reversible arithmetics and a reversible isotherm in between. Okay, so this proof, okay, which is the Clausius theorem, is an extremely important proof in thermodynamics because this leads us to the discovery of property of entropy. Okay, and I had shown you earlier that using this cyclic integral of del Q by T is equal to 0, what ultimately we got was the discovery of the property of entropy, whose change is given by that is delta S. Okay, this change is given by integral of del Q by T, and this is our property of entropy. Okay, I hope you have understood mathematical treatment. I'm not saying very conceptual, but the mathematical treatment of the concept of entropy, how it was discovered and how it is related to the famous theorem known as the Clausius theorem. Okay. Hope you have enjoyed this discussion. Thank you.